Welcome to Submodule 3 of 3, our series on the basics of geosteering. In this session, we'll focus on advanced imaging tools, boundary detection technologies, and the tactics that support effective geosteering. By the end, you'll understand how these methods enhance well placement and optimize reservoir exposure. To start, let's revisit the fundamentals of geosteering. At its core, geosteering involves the real-time adjustment of a well trajectory based on geological and petrophysical data to ensure it remains within a target reservoir. The components of geosteering include geological models, LWD and MWD tools, imaging technologies, and a structured decision-making workflow. Each plays a role in reducing uncertainty as we drill. In terms of techniques, we focus on three main approaches. The first is model, compare, update, a cycle of predicting log responses, comparing them to actual measurements, and refining the model as drilling progresses. The second is real-time dip determination, which uses azimuthal imaging tools to measure bedding dips and resolve structural geometry while drilling. The third is distance to boundary, where advanced detection tools sense formation boundaries several feet ahead of the bit, allowing proactive steering decisions. Finally, success in geosteering is not only about tools, but also about people and processes. Having a skilled, coordinated team is essential. Next, we'll examine the specific methods and how they are applied in practice. This slide consolidates the three primary methods employed in geosteering. Let's continue on with method 2. Dip determination is enabled by azimuthal imaging tools. These provide measurements in multiple directions around the borehole, allowing geologists to calculate bedding dips and strike in real time. This is invaluable in complex structures where dip varies rapidly. Looking at the imaging capabilities available from LWD tools, three key measurements are shown here: resistivity, density, and gamma ray. Resistivity images, such as those from the GVR tool, can deliver 56 azimuthal bins at a resolution of about 1 inch. This level of detail enables the identification of bedding dips, fractures, and thin layers as they are encountered. Density images are typically resolved into 16 sectors with a resolution of about 6 inches. These help us identify lithological variations and changes in porosity. Gamma-ray images provide broader azimuthal coverage, typically in 4 quadrants with approximately an 18-inch resolution. While less precise, they are useful for detecting shale boundaries and correlating with offset logs. Looking at the three images side by side, resistivity at high resolution, density with coarser detail, and gamma ray with quadrant level coverage. From left to right, the increasing coarseness of measurement highlights the trade-off between resolution and depth of investigation. Collectively, these images illustrate how LWD tools provide complementary formation information. The GeoVision resistivity tool, often abbreviated as GVR, is one of the most widely used LWD resistivity images. It provides 5 depths of investigation through laterolog resistivity measurements. Among these, 3 are azimuthal resistivity measurements that generate high-resolution images around the borehole at different depths of investigation. This allows us to map bedding dips and boundaries with precision. The tool also includes a high-resolution focused ring measurement, which sharpens near wellbore resistivity contrast, and a bit resistivity measurement that gives data directly at the bit. Another important feature is the integration of azimuthal gamma ray. This adds lithological context to the resistivity images, helping distinguish between shale, sand, or carbonate facies. The diagram illustrates how shallow, medium, and deep resistivity investigations are acquired simultaneously. The microscope tool is a 4 3/4 inch advanced imaging tool designed to deliver multiple types of measurements in real time. It provides multi-depth borehole images, meaning it can resolve formation features at several radial distances from the borehole. This is combined with multi-depth focused laterolog resistivity, giving a layered view of resistivity contrasts. The tool also includes toroid resistivity measurements, which are non-azimuthal but useful for providing background resistivity trends. Importantly, microscope measures bit resistivity and near bit inclination, giving direct feedback at the cutting face. Azimuthal gamma ray is another feature which, combined with resistivity and density data, provides a high-resolution image of the borehole environment. The ultra-high-resolution image, or UHRI, enhances detail and makes subtle bedding or fracture patterns easier to identify. On the diagram, you can see in yellow the rings for the multi-depth resistivity, the button sensors in the middle, and at the top, the azimuthal gamma ray. Also in the picture, the stabilizer with the UHRI sensor is shown. This tool is an excellent example of integrating multiple measurements into one system. Now, let's move to the topic of real-time image transmission. One of the challenges in imaging while drilling is data transmission rate. This slide highlights the difference between real-time images and memory images. Real-time images are compressed downhole, transmitted uphole through high-bandwidth telemetry, and then decompressed at surface. This process ensures critical image data is available for geosteering decisions while drilling. However, due to bandwidth limits, resolution is typically lower than memory images. Memory images, on the other hand, are stored at full resolution downhole. They can be downloaded once the tool is retrieved to surface, providing a much more detailed dataset for post-well evaluation and reservoir studies. The advantage of real-time imaging is immediacy. Even at reduced resolution, these images allow the steering team to recognize dips, faults, or approaching boundaries without delay. The combination of real-time transmission and memory storage provides both operational value and detailed post-job analysis. On the next slide, we'll see how these images are used as part of a real-time borehole imaging workflow. This slide illustrates how multiple LWD images are combined in real time to support geosteering. Here we see resistivity, density, and gamma ray images integrated with directional drilling data from a power drive rotary steerable system. On the left, the resistivity image shows contrasts that highlight bedding and boundaries. In the middle, the density image provides information about porosity and lithological changes. On the right, the gamma ray image identifies shale intervals. Together, these data sets create a composite view of the borehole environment. The figure is annotated with top and bottom of hole indicators, helping the interpreter quickly orient the images. By analyzing these patterns, the steering team can decide whether to adjust trajectory to remain within the pay zone. This integration of real-time borehole imaging with the BHA is a powerful tool for maximizing reservoir exposure. Next, we'll look at a specific log example that illustrates how reservoir contact varies with and without geosteering. Here is a practical comparison of well placement outcomes. The first well was cut short because it ran out of reservoir, while the second well, drilled with geosteering adjustments, achieved an additional 900 feet of pay. The exposure results are shown as percentages. The third well achieved 79% exposure, the fourth 82%, and with optimized geosteering, the final well increased to 98% reservoir contact. This demonstrates how geosteering significantly improves reservoir exposure by keeping the wellbore within productive zones. By matching modeled responses with real-time data, the steering team was able to recognize boundary approaches and adjust trajectory. Without these interventions, the well would have exited the target sooner, resulting in lost pay. This example highlights the economic value of geosteering. Better exposure means more net pay and higher recovery. On the next slide, we'll look at a broader set of performance metrics comparing drilling outcomes with and without geosteering. Here we can see a direct comparison of well performance with and without geosteering. Let's walk through the numbers. Without geosteering, the net to gross ratio averages about 35%. Total reservoir contact is around 2,500 feet, delivering 900 feet of net pay. Production rates average 4,000 barrels per day, with a productivity index of about 150 barrels per piece ID. With geosteering, those metrics improve substantially. Net to gross rises to 50%, total contact increases to 3,500 feet, and net pay nearly doubles to 1,700 feet. Daily production climbs to 6,000 barrels, and productivity index rises to 250. This comparison shows the quantifiable benefits of geosteering: greater reservoir contact, higher recovery, and improved production efficiency. These improvements translate directly into better economic returns and optimized field development. With that understanding, let's revisit the methods available for well placement and then introduce advanced boundary detection tools. Now let's move on to method 3. Distance to boundary leverages advanced detection tools to see ahead of the bit. These tools detect resistivity contrasts at distances of several feet, enabling proactive steering. Next, we'll focus on Periscope, a game-changing boundary detection service that allows accurate, proactive well placement. Periscope is a game-changing remote boundary detection tool. Unlike conventional resistivity or imaging logs that measure only the borehole wall, Periscope can detect formation boundaries up to 15 feet away. The principle here is directional electromagnetic measurement. The tool sends and receives signals at multiple spacings and frequencies, allowing it to detect resistivity contrasts far from the borehole. This means we can identify approaching formation tops, bottoms, or fluid contacts before the bit reaches them. The graphic shows how periscope coverage compares with other methods. Standard propagation resistivity reaches about 4 feet, seismic tens of feet, while periscope fills the gap with a reliable 15-foot range. This gives geosteering teams a proactive window for decision-making. By mapping boundary positions in real time, Periscope significantly reduces the risk of exiting the pay zone, even in thin or dipping reservoirs. On the next slide, we'll look more closely at Periscope's design features and how it delivers boundary mapping. The key features of Periscope are: first, it is the only LWD tool with 360-degree directional sensitivity. This means it can determine not just how far a boundary is, but also in which direction, above, below, or lateral to the borehole. Second, it has a 5-meter detection range, or about 15 feet. This allows for early warning of approaching boundaries, giving operators time to steer proactively rather than reactively. Third, Periscope provides real-time boundary mapping, detecting both geological and fluid contacts. This includes shale, sand, water, or hydrocarbon transitions. Unlike conventional resistivity tools, it is not simply an imager, but a true boundary mapper. The graphic at the bottom illustrates how the distance to bed boundary enables real-time decision-making to steer a trajectory that keeps it in the pay zone. In essence, Periscope transforms geosteering from reactive boundary chasing to proactive reservoir mapping. Next, we'll see real-world examples of Periscope delivering proven boundary detection results. This slide demonstrates how Periscope delivers proven real-time boundary detection. The tool uses directional electromagnetic measurements with multiple spacings, 34, 84, and 96 inches, and multiple frequencies, including 100 kHz, 400 kHz, and 2 MHz. By combining these measurements, the tool can detect resistivity contrast up to 15 feet from the borehole. This includes identifying 1 or 2 distinct boundaries, such as a reservoir top and a fluid contact. In addition to distance, Periscope provides 360-degree boundary direction, which means the tool not only tells us that a boundary is nearby, but whether it is above, below, or lateral. This capability allows true three-dimensional geosteering. On the right, the images show real-time interpretation, directional arrows indicating the approach of a boundary, with operators adjusting trajectory accordingly. The image below shows the well trajectory as the dotted black line and the reservoir mapping showing the top of the reservoir in dark brown shading. The trajectory is then adjusted to drop and maintain the borehole in the reservoir, whereas if the trajectory were left unchanged, it would have exited. Looking at the benefits of Periscope, it maximizes productive reservoir exposure. By detecting boundaries up to 15 feet ahead, the tool enables operators to keep the wellbore within the pay zone for longer distances. This translates directly into increased net pay and improved hydrocarbon recovery. Another benefit is reducing unnecessary drilling requirements. By steering accurately, we avoid sidetracks or extra hole sections that would otherwise be needed to re-enter the reservoir. This lowers both time and cost. Periscope also helps maximize rate of penetration. With accurate boundary detection, drilling can proceed with confidence, reducing unnecessary hesitation or trial and error steering. The overall result is greater production, achieved with fewer operational risks. The simple diagram on the slide shows shale above, water below, and the reservoir in between. The periscope trajectory holds the bit in the productive interval, maximizing reservoir contact. By staying in the reservoir sweet spot, periscope helps improve overall recovery factor. Longer, more consistent reservoir contact means a higher proportion of hydrocarbons can ultimately be produced. Accurate boundary mapping also supports optimized completion design. With reliable knowledge of top and bottom boundaries, operators can position perforations or inflow control devices precisely, ensuring uniform reservoir drainage. Another important benefit is delaying water coning. By avoiding drilling too close to water contacts, periscope extends the productive life of the well and reduces premature water breakthrough. In turn, this extends well life. Wells drilled with higher exposure and optimized completions produce for longer periods before decline sets in. The diagram again shows the reservoir flanked by shale and water. The periscope-guided well maintains an ideal position within the productive interval, setting the stage for efficient recovery. Periscope contributes to cost reduction and efficiency at surface. By maintaining the well bore within the hydrocarbon-bearing interval, periscope helps reduce water production. Less water means lower costs for separation, treatment, and disposal at surface facilities. Reducing water cut also minimizes the need for water handling infrastructure. Smaller separators and lower treatment capacity requirements translate directly into capital and operating cost savings. Minimized water production means fewer interventions. Wells that avoid early water breakthrough require less workover activity, further reducing operational expenditure. Finally, all of these factors combine to maximize production and overall return on investment. By cutting unnecessary water and keeping the focus on hydrocarbons, periscope wells deliver better long-term economics. This final benefits slide highlights the operational risk reductions offered by periscope. By detecting formation boundaries in advance, the tool helps avoid unstable formations that can trap or damage downhole equipment. This reduces the likelihood of stuck tools, saving costly fishing or sidetracking operations. Periscope also minimizes the risk of unnecessary sidetracks. Traditional geosteering methods often require corrections once a boundary has already been crossed. With periscope's proactive detection, trajectory changes are made early, avoiding costly course corrections. Another advantage is avoiding slow drilling through non-productive formations such as shales or tight carbonates. By holding the well within the pay, drilling progresses at higher ROP with reduced bit wear. Ultimately, these risk reductions mean fewer surprises, lower non-productive time, and more consistent drilling performance. The diagram again shows shale above, water below, and reservoir in between, reinforcing the idea of accurate steering away from trouble zones. With periscope's benefits established, let's now introduce Geosphere, another boundary mapping technology with its own advanced capabilities.
Geosphere Reservoir Mapping While Drilling Service. The Geosphere Reservoir Mapping While Drilling Service reveals fine details about the reservoir more than 100 feet from the wellbore, using a directional transmitter and 2 receiver subs. Dual-frequency directional electromagnetic signals are sent from the transmitter into the formation. The 2 receiver subs retrieve the signals. The receiver subs can be placed anywhere in the borehole assembly up to 100 feet from the transmitter. By increasing this distance, the depth of investigation is also increased. Data is then transmitted to the surface in real time for interpretation by Schlumberger and customer asset teams. With the Geosphere Reservoir Mapping While Drilling service, operators can accurately determine subsurface layers and fluid boundaries. This results in maximum reservoir exposure during landing and steering operations, and refinement of field development plans for improved production potential.
This slide brings together the key tactics that underpin effective geosteering. First, we must establish the required precision based on formation, thickness, and geological complexity. Thin reservoirs demand higher resolution tools and closer steering control. Second, disciplines must be organized into a geosteering team. Success requires collaboration between geologists, petrophysicists, drilling engineers, and directional drillers. Third, structural and trajectory data must be continuously converted into a usable real-time model. This ensures the entire team is working from a common picture. Fourth, three-dimensional aspects of geology must be quantified. Dips, azimuths, and faults all affect well placement. Fifth, sensors must be located at or near the bit to reduce uncertainty. Relying on distant resistivity measurements introduces lag and increases risk. Sixth, procedures for azimuthal testing and calibration must be in place to validate measurements. Finally, strong communication links must be prioritized and maintained within the team and with decision makers. With these tactics in mind, let's review the objectives of this module and confirm what we've achieved. Let's revisit the learning objectives and confirm how we've met them. Our first objective was to define geosteering. We reaffirmed that geosteering is the real-time adjustment of a well path based on geological and petrophysical data to maximize reservoir exposure. The second objective was to explain the basic principles of geosteering. We did this by walking through the workflow, building geological and property models, generating forward logs, matching real-time data, and updating models continuously. The third objective was to review geosteering methods. We compared model compare update, dip determination, and distance to boundary, highlighting the strengths and limitations of each. The fourth objective was to introduce advanced imaging and boundary detection tools. We covered GVR, microscope, and periscope, showing how each improves real-time interpretation. We also touched on Geosphere, which extends detection into true reservoir mapping. Finally, we summarized the tactics for successful geosteering, emphasizing team structure, real-time modeling, 3D quantification, and strong communication. With these objectives addressed, you now have a full picture of both the basics and the advanced practices of geosteering. This concludes Submodule 3 of the Basics of Geosteering. Please proceed to the short quiz to test your understanding of the material. Thank you for your time and attention throughout this session, and I look forward to continuing with you in the next stage of training.